Here's a trick that made embeddings famous. You take the vector for king, subtract man, add woman, and you land somewhere near queen. It looks like algebra doing language. It isn't magic, and it isn't always true. But it is the first time a lot of people saw that meaning can sit in a list of numbers. By the end of this, you'll know what that list of numbers actually is. Why nearby words sit near each other in a space nobody drew by hand. Why the same spelling can mean two different things, depending on the sentence. And how search by meaning works, which is the piece sitting under retrieval and under a lot of what people now call RAG. Here's the part that surprises people. A computer does not know that cat and kitten are related. To it, those are two different strings. One is CAT, the other is KITTEN. Sharing letters would help a little, but dog and puppy share almost none. So if you want a machine to treat them as similar, spelling alone does not encode semantic similarity. You have to store something else, a representation that two related words can share even when they look nothing alike. That something else is a point. Each word gets a list of numbers, usually a few hundred of them, and that list is its address in a space. Cat sits here, dog sits nearby, and kitten sits near both. Table sits somewhere else entirely. Distance in that space is the whole idea. Near means related, and far means not. Nobody drew the map. The numbers found their own places. Nearby is doing the real work. Words that show up in the same kind of sentences end up close. Cat, dog, kitten, puppy sit in one neighborhood. France, Paris, Europe sit in another. The model never got a dictionary definition for any of them. It got a lot of text, and the geometry is what fell out of that. And far away is just as important, because if everything sat in a pile, the space would tell you nothing. Table is not near cat. Bandwidth is not near kitten. The useful claim is not that two words are similar. It is that the space can tell similar from not, without anyone writing a rule for either pair. That is a much cheaper thing to learn than a dictionary, and it generalizes to pairs nobody ever labeled. Now the picture in your head is two dimensions, because that is what fits on a screen. Real embeddings are not that. A classic word to vector is 300 numbers. Modern sentence models often sit at 384, or 768, or 1536. You cannot draw that many axes. You can still measure the angle between 2 points, and that measurement is what the rest of this lecture uses. Before this, the obvious encoding was one hot. One slot per word in the vocabulary, a 1 in that slot, zeros everywhere else. Dog and puppy are then exactly as far apart as dog and democracy, because every pair of different words is orthogonal. A dense embedding throws that away. A few hundred numbers, almost all of them non-zero, and the geometry is allowed to mean something. Same vocabulary. Completely different object. And now distance can finally stand in for relatedness. The usual measure is not a ruler on a page. It is the angle between two vectors, cosine similarity. Point the same way, and you get a number near 1. Point opposite, and you get near -1. Orthogonal near 0. Length gets divided out, so a longer vector is not automatically more related. That is why cosine similarity is one of the most common measures used for embedding search. So how do the numbers get set? Nobody types the coordinates in. Training makes useful words predictable from their context. Given a stretch of text around king, queen or throne or man tend to show up nearby. When the guess is wrong, you nudge every number a little in the direction that would have made the real neighbors more likely. Ask the same context again, and those neighbors come back higher. After enough text, words that shared company share a neighborhood. The classic version of that job is skipgram. You show the model one word, and you ask it to predict the words in a small window around it. Not the definition, not a synonym list, just what tends to show up nearby. That is a much cheaper question than understanding, and it turns out to be enough to grow a useful space. CBOW does the reverse, predicting the center from the window. Same idea flipped. Here's the part that still feels strange to me. The vector was never the goal of that training job. The goal was to predict nearby words. The embedding is the address the model invented so that prediction would work. Meaning in this picture is a side effect of a guessing game. Nobody sat down and assigned cat a location, which is why the algebra sometimes works. King minus man plus woman lands near queen, because the shift from man to woman is a direction in the space, and king sits a similar shift away from queen. It is a famous demo. It is also brittle. It depends on the training text, the word frequencies, and which sense of the word you landed on. Treat it as a picture of the geometry, not as a proof that the model understands gender or monarchy or anything else. The papers that made this famous also showed plenty of pairs where it fails. And that last point is the real limit of a static embedding. Bank has one vector. River bank and money bank both have to share it. The geometry averages the senses, so the point sits somewhere in the middle, which is a place no actual sentence ever meant. A tall similarity to bank is not a fact about which bank you had in mind. One address per spelling is the whole constraint, and English is full of spellings that do not deserve one address. So the next idea is almost forced. Stop giving a word one address for its whole life. Give it an address in this sentence. Same spelling, different neighbors, different point. That is a contextual embedding, and it is what modern models actually produce when they read your prompt. Word2Vec could not do this. A transformer can, because it reads the whole sentence first. Take two sentences. I sat on the river bank. I deposited cash at the bank. The word bank is the same string both times. After a contextual model has read the sentence, those two banks are different vectors. River pulled one of them toward water. Deposited and cash pulled the other toward a building. The spelling never changed. The point did. And that is why a static table of word vectors was never going to be enough, once the job became reading a whole sentence. Most of the time, you do not want a word. You want a sentence, or a paragraph, or a chunk of a document. You can average the word vectors, and that works better than it sounds. Dedicated sentence models do a better job, because they were trained to pull paraphrases together and push unrelated sentences apart. That is the vector you actually store when you build a search index. 1 point per passage, not 1 point per word. And once you have that, search no longer has to be only a string match. Once a sentence is a point, search no longer has to depend only on keyword matches. You embed the question. You embed every passage you might want back. Then you ask which stored points sit nearest the question. How do I reset my password can find the article that says recovering a locked account, even if those words never appear. That is the whole move, and it is why people started putting embeddings under search. Keywords still help. Meaning is what catches the rest. That is the retrieval half of RAG. You do not dump the whole library into the prompt. You fetch the few passages whose embeddings sit nearest the question, and you hand those to the language model as context. The generator still writes the answer. The embedding is what decided which passages it received. If retrieval misses, the model cannot cite what it never received. So a lot of what looks like a generation failure is a nearest neighbor failure one step earlier. Fix the index before you blame the pros. which means what you embed is what you can find. Embed a whole chapter as one point, and the useful sentence gets averaged away. Embed every line, and you retrieve fragments with no context. Chunking is the unglamorous decision that makes the rest of this work, or fail. At larger collections, you usually do not want to scan every vector on every query. A vector store keeps an index, usually something like HNSW. Search walks a few graph hops and comes back with approximate nearest neighbors in milliseconds. Approximate is the honest word. You trade a little recall for speed, and at a few million chunks that trade is the whole product. Exact search still exists. It just gets expensive as the corpus grows. Dimensions are a budget. 384 numbers per chunk is light. 1536 is heavier and often a bit sharper. Storage is count times width. A million chunks at 1536 dimensions, at 2 bytes each, that is FP16, is about 3 gigs for the vectors alone before the index. FP32 would be about 6. Check before you scale the corpus, because the index can cost as much again. And do not mix 2 models in the same index, because they do not live in the same space. The obvious question is which model. For English retrieval, BGE and E5 are strong open starting points. Nomic is a common local choice. Hosted, OpenAI and others sell an embed endpoint. Start with a small multilingual model if you need more than English. And do not mix vectors from 2 different models in the same index, because they do not live in the same space. Re-embed the corpus if you change the model. The interface is almost boring, which is the point. You send text, you get back a list of floats. You embed the query, then embed your document chunks, usually in batches when you build the index. The exact request format depends on the model. With Nomic, for example, queries and documents use different task prefixes. Miss the prefix and retrieval gets worse. What comes back is still the same basic thing, a vector, an address you store next to the original text. A high cosine is not a fact. It means the model thinks these 2 strings live in a similar neighborhood, given the text it was trained on. Near is not true, and it is not relevant to your user unless you check. Same failure mode as a tall probability bar, just in a different space. One last expansion, because the space does not have to be words. With a multimodal embedding model, clip in models like it put an image and a caption into the same geometry. Search a photo by typing red bicycle leaning on a wall, and you are not matching pixels to letters. You are asking which image point sits nearest that sentence point. Same nearest neighbor job. Different kind of object. And that is why multimodal search can work without a caption on every file. So where does that leave you? 3 things, really. A word or a sentence as a point. Near meaning related, measured by an angle. And a retrieval loop that uses that geometry to decide which evidence reaches the language model. That is the whole stack under search by meaning, and it is sitting in every RAG demo you have seen. One last thing, because we skipped how a modern model actually builds that contextual point. I told you the neighbors change the address, but I never told you how the model decides which neighbors matter. Take a sentence like down by the river bank. By the time the model reaches bank, the word river is what settles which kind of bank you meant. That mechanism is called attention. It is one of the key mechanisms that makes transformers work. Next time the transformer,